and welcome again to my Physics Online video lecture series. In today's video, I want to talk a little bit about the buoyant force. So this is a video that is a continuation of my discussion of fluid statics, which is of course a part of the larger discussion about fluids for a Physics 1 course. The fluid statics basically stuff that you got to know in order to make this video work out includes a few things that we will need to recall. So first and foremost, if you are working in statics, then you are looking at equilibrium, and that implies that the net force acting on a given object is zero. Second, we have that fluids exert pressure, and the pressure depends on depth within a fluid. So it depends on depth, and usually we write that as P is equal to rho times G times H, where this right here is your fluid density, and your H represents the depth within the fluid. Also worth noting about pressure is that pressure tends to be perpendicular, so it tends to be perpendicular or normal to surface upon which it is applied. This means that, among other things, it pushes upwards on the bottom of an object if it's a flat bottom, and it pushes side or side on the sides, and it pushes downwards on the top of an object. And this part is really the part that's relevant to today's discussion. So let's, for a moment here, assume that I have like a container, and in the container happens to be some fluid like water or something like that. And now I have an object which is somehow floating within this container. So a block, for example, and the block maybe looks more or less like this, and the water line near this block might be like so. Okay, well, the logic of pressure being perpendicular to the surface upon which it is applied is that I have some pressure in these directions from the sides, and it's basically the same amount of pressure from each of these sides. So net force between those different pressures is zero. And then I also should have pressure acting upwards on the bottom of the object, but there's no pressure on the top, P equals zero, up here, or zero relative to the atmosphere background pressure, if you will. So this means that this object has a total force. If I was going to draw the object like from a side view, I have M times G acting downward, and then I have pressure acting upward on the bottom of it. And so this upward force, the buoyant force, looks like the pressure times the area of the bottom of this object. Now, the object may be partially submerged as drawn above, but it could be totally submerged as drawn below. So if I have it totally submerged, then again all the lateral forces will balance, all the lateral pressures will balance, and I have some upward, we could call this like the upward pressure from the bottom, and I have a downward pressure from the top. And so Again, my buoyant force, F buoyant, would look like the upward pressure minus the downward pressure times the cross-section area of this block. Well, coming back over here to this whole P is rho times G times H, this becomes rho of the fluid, so we'll say rho fluid, G times delta H, difference between height in depth between the top and the bottom. But if we just simply say that this right here has a height h, then we can still say rho g h or rho g delta y. So this one right here might be like a y. And so a difference in pressure, delta P, would be rho g delta y. But delta y is just whatever the height of the object is. Put differently, from the top of the fluid to here might be y1, and from the top of the fluid to down here might be y2. And so delta y, y2 minus y1 is just the height. All of that is times the cross-section area A. But this right here just is the volume of the object which is submerged. So I've basically obtained a buoyant force in terms of the fluid and object properties. The buoyant force is the volume of the object which is submerged. So we could say volume object submerged times G times the density of the fluid. So that gives you your buoyant force. Now that's the typical derivation, maybe not in those exact words, but more or less that's the gist of the general derivation. There's a second way of looking at it, which is sort of the equilibrium approach. And this is the approach that is usually not used in textbooks. It's maybe a little bit harder to conceptualize, but if you understand it, then it actually can be used to sort of quickly answer or understand a variety of other problems that you can do with this. For example, those of you who are watching this video because you're trying to study for something like the MCAT, you've maybe seen practice problems about what happens if you have an ice cube floating in water on the Earth, and then maybe you take it to the moon. Is it floating higher or lower or the same depth in the water? That kind of thing. So this conceptual example here says I have fluid and it's at equilibrium. So all the fluid in this container is at equilibrium. That means that it's all totally still. I'm going to pick a sample of the fluid. This little dashed lined box basically represents some volume of the fluid. So this right here is some fluid. And this fluid has, we know, a force acting on it from gravity downward of mass fluid times G, or in other words of density of fluid times volume of fluid times G. Okay, that's fairly straightforward. Everything is at equilibrium. That means that I have to have a net upward force, we'll call this the buoyant force, FB, acting on that little section of fluid, such that FB is equal to mass of fluid times G, or in other words, it's equal to density of fluid times the volume of the fluid times G. This is the condition implied by equilibrium, sum of forces being 0. Now, suppose that I replace this volume of fluid, and I'm going to draw this in a different color. Suppose that I put an object right here that exactly fills in this volume of fluid that I have removed. Okay, so I replace the fluid that's in here with some object. So red represents some object. All right. Well, the rest of this fluid is at equilibrium, and therefore by removing this much liquid and replacing it with some other object, I can't have affected what the rest of this fluid is doing here. And that means that I continue to have an upward force, a buoyant force, but now that buoyant force is applied to the object rather than to the fluid that I've sort of displaced by that object. So this object displaces fluid. Well, that buoyant force still has to be FB is equal to rho fluid times volume of fluid displaced times G. But that's just the same thing as the density of the fluid times the volume of the object times G. Now what's so neat about this second approach is, let's go back to that question about there being, let's say like an ice cube floating in water on the Earth versus the same ice cube in the same water but on the Moon where there's 1/6 as much gravity. Well, if you attempt to answer the question just by looking at what does the buoyant force do over here, what you end up seeing is, well, G has gone to 1/6 of its original value, and so the buoyant force is lower than it started with, and so maybe the object is now sinking, or it doesn't float as high in the fluid. And on the other hand, you might trick yourself by saying, well, there's less gravity, so the object has less weight, so the object floats higher. Well, with this other approach, it should be evident that both the fluid that you've displaced, the weight of that fluid displaced, which gives you the buoyant force, and the weight of the object, both things are reduced or increased by the same factor of G. And that in turn means that the decrease in weight of the object and the decrease in the weight of the fluid that's surrounding the object are by the same factor, and therefore this buoyant force will be the same fraction of the object's weight as it was before. Now for an object which is at neutral buoyancy, that basically means it remains at neutral buoyancy. For an object which is floating near the top, that means that the object will still float near the top and will have the same fraction out of the fluid as it did before. So let's maybe do a quick example. For our quick example, we want to know how much buoyant force acts on a block of aluminum which is 5 centimeters to a side and which is totally submerged underwater, given that water has a density of 1 gram per milliliter, which, as we know, is equivalent to 1,000 kilograms per meter cubed. So this is your density of your fluid. This right here, we're assuming, of course, this is in Earth gravity. This right here is like the length of a side. The volume of such a block will look like length cubed, which is 125 centimeters cubed, which is 1.25 times 10 to the minus 4 meters cubed. Our buoyant force is thus rho of fluid displaced times volume of the block times G. Therefore, our buoyant force is 1,000 kilograms per cubic meter times 1.25 times 10 to the negative 4 cubic meters times 9.8 newtons per kilogram, which gives us a total of 1.225 newtons worth of buoyant force. If we round that off to two significant figures, this buoyant force is approximately 1.2 newtons. So that's it for that simple example. That's all actually for today's video. Hopefully you've learned something from watching it, and as always, thank you for watching.